Hello everybody, welcome to section 2.6 on the algebra of functions, and our job right here is pretty straightforward. We want to be able to combine functions by adding, subtracting, multiplying, and dividing, and determine domains of those compositions. We're also going to be dealing with something called a composition of functions, and in a composition of functions we also want to determine the domain of those resulting compositions. And then finally, we're going to be able to determine something called a difference quotient of a function. So those are the three major items that we have on tap right here. So let's begin with operations of functions. When I say an operation, in algebra, an operation is always considered to be an addition, subtraction, multiplication, or division, or some other combination of those things. And just like there's an algebra of real numbers, there's an algebra of functions. So here's some notation that you will definitely need to know. When we're adding two functions, an f of x plus a function g of x, we indicate that by adding f plus g of x. So this is our notation. F plus g of x means the actual addition of one whole function to another whole function. As an example of that, if I were to tell you that f of x was a function like 2x plus 1, let me get an equal sign in here, 2x plus 1, and that g of x was a function like, let's make it a nice simple 3x, then saying f of x plus g of x means that we actually add these two functions directly together, 2x plus 1 added to 3x. So in other words, f plus g evaluated at x is equal to 5x plus 1. And all we're doing is combining those functions by adding them together directly. We also have subtraction of functions, f of x minus g of x, which we indicate as f minus g of x, or just simply f minus g. We have the function f of x times g of x, which we'll indicate as f times g of x, or simply fg. And f of x over g of x, which is designated as f over g of x, or f over g, provided that g of x is not equal to 0. Now, one other quick note is determines the domain. And whenever we combine two functions by addition, subtraction, multiplication, or division, we take the intersection of the two domains, except in the case of division, where the intersection cannot include any point where the domain of the denominator would be 0. So let's go through and let's try this out with a real function or two. Let's say that I've got two functions, f of x plus g of x, f of x and g of x. F of x is x squared minus 25. G of x is equal to the square root of x plus 3. So before we even begin, we're asked to find the domains of f plus g, f minus g, fg, and f over g. We want to know the domains of f and g already. So let's talk about this. What is the domain of the function f? This is my notation for domain of f. And in this case, it's a polynomial, x squared minus 25. There are no restrictions put on the function purposely, so we'll say that the domain right here, and I'll use set builder notation, is the set of all x such that x is any real number. So negative to positive infinity, that's our domain right here for f of x. How about the domain of g? Well, this is a radical function, and if you recall anything about radical functions, we need to determine the domain by setting the quantity under the radical greater than or equal to 0. So if we set x plus 3 greater than or equal to 0 and solve for x, we're going to find that x is greater than or equal to negative 3 constitutes our domain. So now let's talk about these combinations of functions. What could we say? Well, first of all, f plus g of x this is the designation for simply adding these two functions together, is going to be equal to x squared minus 25 plus the square root of x plus 3. Very simple. What would be its domain? Well, if the domain is the intersection of the domain of f and g, the intersection of these two domains is equal to the domain of g. So our domain of the combination of f plus g is going to be equal to the intersection of the set of all real numbers with the domain x greater than or equal to negative 3. But we don't usually write it this way. What we're going to do is we always shorten this down to its simplest form. So our domain right here is going to be all x such that x is greater than or equal to negative 3. Move that over right here. Let me write an actual 3 right here. 3. All right. Well, how about f minus g of x? Well, f minus g is practically the same thing as what we just saw before, only this time we're going to subtract the two functions x squared minus 25 minus the square root of x plus 3. Its domain is also the same as the above, the intersection of these two sets. So the set of all x starting from negative 3. How about f times g? Well, f times g of x, just as we indicated before, is going to be the intersection of our two sets. So we're going to have the quantity x squared minus 25 times the square root of x plus 3. So our domain of f times g will also be the set of all real numbers x such that x is greater than or equal to negative 3. All right, one more. Let's talk about division f over g of x. What happens here? Well, in this case, when we divide the two functions, we do have to make an important distinction between division, x squared minus 25, and multiplication and the other operations, in that we have a denominator of this function, and we note that the denominator would be equal to 0 at x equals negative 3. Since x equals negative 3 cannot be included, we might write the domain of f over g as being the set of all x such that x is greater than or equal to negative 3, just like our other intersections, and x cannot equal negative 3. And rather than writing out this whole big long string, we'll just note that, well, if x cannot equal negative 3, then the greater than and equal symbol does not apply, and we'll write that x such that x is greater than negative 3, but not equal to negative 3, is our domain. So you do have to be very careful to ensure that you do not include values that make the denominator equal to 0. Other than that, these operations are very straightforward and simple.